I'd like to go through some practice problems in Chapter 5. Again, just pause the video as you need to and give yourself a chance to work these out as you're watching. We'll just go ahead and start. This is example 5.1. Write Lewis dot symbols for A, a fluoride ion F-, B, potassium ion K+, and C, the sulfide ion S2-. Strategy here to do these Lewis dot symbols for the elements, you're going to use dots if you have ions, specifically anions, which are negatively charged, and you will remove dots for cations to achieve the correct charge. The key thing first, before you know how many electrons you'll need to add or remove, you need to understand the valence electrons for the elements that you're looking at. Also, if it is charged, you'll usually put brackets around it and then the charge on the outside of it or inside of it. There's different ways to write it, so let's just take a look at those. Alright, so for part A, we know that fluorine usually has 7 valence electrons, so that would represent 7 dots. When fluorine is negatively charged, because electrons carry a negative charge, we will add an additional dot. So instead of 7 dots, we're going to have 8, and you can see we have 2, 4, 6, 8. And usually you can just surround it top, bottom, left, and right, and this model just looks nice and organized. The brackets go around the fluorine, and then a negative charge to state that this is not neutral fluorine, it's actually the anion version of it. For part B, which is potassium, potassium usually has 1 valence electron. However, because it has a positive 1 charge, positive 1 charges would mean that we have less electrons. That would give 1 more proton than electron than a usual neutral potassium. So we remove that 1 valence electron. It's not shown. Use the symbol of K for potassium and then a plus charge. And again, you can put brackets around it if you want. A lot of times when there's no valence electrons, you can just put a plus as they've done here without the brackets. But either way is fine. For part C, this is sulfur, which usually has 6 valence electrons, being in group 6, but however with the negative 2 charge, that's letting us know that it has 2 extra electrons. So you could draw the 6 on there and then add the extra 2. You'll have 2, 4, 6, 8 electrons. Put brackets around it just as you did for fluorine. And then a negative 2 charge. A lot of times when the charges are written, if it's more than 1, you actually need to write that numeral. So you'll notice with the fluorine, a 1 is not written. With the potassium, a 1 is not written. But with the sulfur, we need to specify it as a 2. And a lot of times just in general, how they'll do the models, they'll put the number first and then the charge, so 2 minus. If it was a plus charged cation, then you could write 2 plus. So think about it. Here is for ions that are isoelectronic with noble gases, meaning they have the same charge, the cation should have no dots remaining around the element symbol. The anions are going to have more dots, and they should have 8. Unless it is something that is trying to match up to be like helium. The purpose of gaining or losing electrons as we start to look into bonding is to achieve a perfect electronic configuration. A perfect electronic configuration meaning those that are like the noble gas. Note that for anions we put square brackets around the Lewis dot symbol and place the negative charge outside of those brackets. And also, because the symbol for a common cation, such as the potassium ion, has no remaining dots, then square brackets are not necessary. And then as I mentioned on the last slide, sometimes people just put them in there. Different models will put them in there. And that's okay. Our second example is going to look at lattice energy. This is asking arrange MgO, which is magnesium oxide, CaO, calcium oxide, and SrO, strontium oxide, in order of increasing lattice energy. Increasing lattice energy, so we would start with the lowest, and then which one is in the middle, and then the highest. So we're going to go from lowest to highest. The strategy here would be to consider the charges on our ions and also the distances between them. We can apply Coulomb's law, we borrow that from physics, to determine our relative lattice energies. Since all three compounds contain oxide, which is O2-, that means all three of the cations to balance out will need to be +2. Recalling that lattice energy will increase as the distance between ions decrease, we need only to look at the radii of our cations. So reason why is because all three contain the same anion, the O2-. So we can examine the cationic radii and look at the relative sizes of those. So from a chart, you could look these up, and the sizes of these in angstrom, which is 1 × 10⁻⁻10 meters, are 0.72 angstroms for our magnesium +2 cation, right at 1 angstrom for our calcium +2 cation, and 1.18 angstroms for our strontium +2 cation. So because of those sizes, our order is going to be strontium oxide, calcium oxide, and magnesium oxide. So strontium oxide is the lowest lattice energy, and magnesium oxide is the highest lattice energy. The size of it, magnesium oxide is the smallest distance, so it would have the greatest energy, whereas strontium oxide has the largest distance, and that would be the lowest energy. And then one more thing to think about before we go on is we can see that magnesium, calcium, and strontium are all in the same family or group. They're in column 2A. So we know and can predict their result without even knowing the actual angstrom size from the table. We can just see as you go down the periodic table, atomic radii get larger. As you go across, they get smaller. But in the same group, we're going to go from the magnesium, calcium, and strontium. Their relative lattice energies, just to look at these, is 3,217. All of these are in kilojoules per 1 mole of the compound. So strontium oxide, 3,217. Calcium oxide, 3,414. So again, they're increasing. Magnesium oxide, 3,890. So as you go down the periodic table, you can see the lattice energy will decrease. That's a nice trend to remember. Another thing that's important to practice and know how to do is naming. We can break apart naming into different categories. The major two categories are ionic compounds and covalent compounds. We'll start with ionic compounds. An ionic compound will pair together a metal with a nonmetal. The metals are usually positive and the nonmetals are usually negative. So it's easy to remember metals positive, nonmetals negative. The metal is written first, the nonmetal is written second. Use the symbols from the periodic table that we're familiar with. The subscripts represent how many we'll use of each so that you'll have a charge balance. We want to have neutral compounds. The reason why these elements will bond together is so that they can attain a very stable electronic state. And again, that state is just like the nearest noble gas. All right, now let's practice with the naming. We have A, which is CaO, B, MgN2, and C, Fe2S3. We want to identify the cation and anion in each compound. As I mentioned, the cation is written first, which is the metal. The anion is written second, which is the nonmetal. You will just state the name of the metal from the periodic table, And for the anion, you're going to use usually about the first syllable of it and then add an IDE ending. So it will have an "ide" ending. Sometimes when we have metals, there are some that are multivalent, meaning that they have more than one possible charge. There's a handful of them, and they're all within the transition element area, transition metals in the middle. If we have a metal that can have more than one charge, we have to specify that using a Roman numeral. You'll actually see that in just a moment. So for our solutions A, B, and C, CaO is calcium oxide. So we name the metal outright, which is calcium. We drop the "igen" from oxygen, just use the ox, and give it an IDE ending, calcium oxide. Part B, our metal is magnesium, so we just state that outright. The nonmetal is nitrogen. We use the nitr, the NITR, give it an IDE ending, and it's magnesium nitride. Now for part C, you'll notice that it's slightly different. We have iron, which is one of the transition metals that is multivalent. There's only a handful of them, and once you practice them, you'll be able to recognize which ones they are. Iron is probably the most commonly used multivalent metal in example problems. Iron's charge states can either be +2 or +3. We need to examine the sulfur and figure out what charge the sulfur has, how many we use, to be able to deduce the charge of the iron. Sulfur is in column 6. It's 2 away from the noble gases, so to get a perfect electron configuration, it needs to gain 2 electrons. It usually will have a -2 charge. So with the sulfur that has a -2 charge, we can see in this formula that was given to us, we use 3 of them. So the negative charge would be 3 times -2. So this half of the molecule is worth a -6 charge. Now we know that this will be neutral. So for this to work, our positive half of the molecule needs to be +6. And we use 2 irons. And so if there's 2 irons and both of those are going to equal up to a grand total of +6, that means that each one of these needs to have a +3 charge. For ionic compounds, they won't have differing charges. You won't have an iron 2 and an iron 3. They'll either be both iron 2 or both iron 3. They'll have the same charge. So we have 6 divided by 2. That gives us 3. Now we can't just say iron sulfide because iron's multivalent. Calcium oxide, magnesium nitride. Calcium is not one of the transition metals. It's in the second column, so is magnesium. Our alkali earth metals, they only have one charge. It's always +2. So you don't have to specify the Roman numeral. But with iron, because it's +3, we're going to put in parentheses 3 lines, which just represents the Roman numeral 3. And so this would read iron 3 sulfide. Write those out again and just take some time and make sure you convince yourself why we use the Roman numeral here, but not in A or B, before you keep going. One thing that I want to mention is be careful not to confuse the subscript in the formula with the charge in the metal ion. So for example, the subscript on iron is 2, but it's an iron 3 compound. You don't use the subscript value inside the parentheses. You use whatever the charge is of it. So sometimes people can flip-flop those. So this represents the charge and not how many we used. For example 5.4, we're going to go backwards, go from name to formula. So this reads, deduce the formulas of the following ionic compounds. Part A, mercury 2 chloride. Part B, lead 2 bromide. And part C, potassium nitride. The nice thing about going from name to formula is that you can already see what the charge is of it. So we know that because this is a Roman numeral 2, mercury is one that's multivalent, but it already tells us here that this is +2 mercury. Same thing with lead 2 bromide. Lead can be multivalent as well. This 2 says that lead is +2 in this case. So we can actually write this charge and then figure out how many anions we'd need. And then potassium nitride, we don't need a Roman numeral because it is just one charge. It's +1. It's in the first column. So again, the strategy: identify the ions in each compound. Figure out how many you'll need of each so that you'll have a neutral charge. You want to figure out what's the plus charge and what's the minus charge of our compound. Use subscripts to use more than one of that element. All right, so part A, mercury 2 chloride. We know that we have mercury +2. Find mercury in the periodic table. You can see the symbol is Hg. We have a +2. Chlorine in the periodic table is 1 away from the noble gases. It's a nonmetal. It's a negative charge. It needs to gain 1 electron. So it's Cl-. Now we have a +2 and a Cl-. We need to find the lowest common denominator between the two. It's pretty easy when it's 1 and 2. You need to get to 2. So to get to 2, we need to have 2 chlorines. So if you need to, write out Hg +2, and then write out Cl-, and write out a second Cl-, and then you can add up the total to see that 2 of the chlorines would have a -2 charge to balance out that +2 for the mercury. So our formula will be HgCl2. For part B, lead 2 bromide, we're going to do this the same exact way. It's going to end up with the same formula. The lead 2, we find lead in the periodic table is Pb with a +2 charge. Chlorine is constant, it stays -1. We're going to need 2 chlorines to combine with the +2 charge lead. That will give us a formula of PbBr2. Potassium nitride, we don't have a multivalent metal. We just look in the periodic table, see that it's in group 1. It's a positive charge. Nitrogen, we can see is in group 5. It's 3 away from our noble gases, so it would need to gain 3 electrons to be like the nearest noble gas, so it has a -3 charge. To get the positive and negative to balance, we're going to need to use not 1, not 2, but 3 potassiums. We use 3 potassiums. That would be a +3 charge to balance with the -3 charge. And this gives us a formula of K3N. Not too bad. Usually people like to go from name to formula over going from formula to name, but be able to go both ways. Make sure that our charges balance out and that we get an overall neutral charge as well. All right, example 5.5, write the molecular formula of ethanol based on its ball and stick model shown here. You've probably worked with ball and stick models before as you've gone through and reading the book. Usually the red spheres represent oxygen, the little white spheres represent hydrogen, and the black spheres represent carbon. So if you didn't know that, then make sure you write that down and remember the white ones are hydrogen, the black ones are carbon, and the red ones are oxygen. The molecular formula is going to write out the element and how many you have of each one. And then there's a usual trend with it, and just with practice you will figure out the order to write these in, like which one comes first. Do I write oxygen first, hydrogen first, carbon first, or so forth? So refer to the labels on the atoms. So what color represents the element? There are 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom. So our solution is C2H6O. Usually the less electronegative element is written first, And a lot of times we'll have carbon-hydrogen compounds, and you'll see that carbon is pretty much always written first in a molecular formula. If we have a CHO compound, a compound that contains a certain amount of carbon, hydrogen, and oxygen, it'll usually be in that order: carbon first, hydrogen second, oxygen third. So one thing to think about before we go on, often the molecular formula for a compound such as ethanol, which consists of a carbon, hydrogen, and oxygen, is written so that the formula more closely resembles the actual arrangement of atoms in the molecule. So one other expanded molecular formula could be written C2H5OH. And this actually does show an alcohol, and this is just a little bit further into thinking about it, is what's called a functional group. A functional group is unique elements together that have similar reactivity. Alcohol is one of those functional groups. It is an oxygen bound directly to a hydrogen. And so this is separating off the carbons, hydrogens, and then the oxygens. Another way that we can write this that even further distinguishes how it is written would be to say, and I'm just going to pretend this is backwards. So pretend this is on the left and this is on the right. This would have a carbon with 3 hydrogens, a carbon with 2 hydrogens, and an oxygen with 1 hydrogen. So we could say CH3, CH2, OH. And so if you write that out, CH3, CH2, OH, you can see exactly how it's bound together. Let's do one more example, and we'll do this in multiple parts so that you don't have one long video to watch. So worked example 5.6. Write the empirical formulas for the following molecules. A, glucose, and the formula is C6H12O6, and that's a substance in our blood. It's known as our blood sugar. Part B, adenine, is C5H5N5, and this is known as vitamin B4. And part C, nitrous oxide, is N2O, and it's used in the dentist for laughing gas, and it's also used as a gas in different types of aerosol applications, such as whipped cream. So it makes the whipped cream come out fluffy rather than just come out kind of like a just ooze out liquid. Our strategy for an empirical formula. The empirical formula is the smallest whole number ratio, so that you find the lowest common denominator and divide each of them by that, and that will be your empirical formula. The empirical formula needs to be whole number. So for part A, we can divide each of the subscripts in the molecular formula by 6. It's C6H12O6. The lowest common denominator is 6. This would give us an empirical formula of CH2O. So carbon and oxygen are in the same ratio. There's both 6 parts of them. And then hydrogen, there's 12 parts of them. So carbon and oxygen are 1 to 1, whereas hydrogen is 2. So our ultimate ratio here is 1 to 2 to 1. If we divided the subscripts by 2 or 3, and you may do this as you're working through, you can get C3H6O3. When you examine this a little more, you can see the 2 3s, so you know that you could just divide by 3 again to get C1H2O. So you want to get the lowest common denominator without getting any fractions. If you divided by 3, it would take you down to C2H4O2, but you can see carbon and oxygen, there's 2 of those. You got to keep going further. You want to get the lowest common denominator. So for part B, and let's remind ourselves what B was, we have C5H5N5. This one should be straightforward. You can see that they're all 5, right? So this should just be CHN. You divide by 5. And the last one, don't look too deeply into it, is N2O. And the lowest common denominator with the oxygen has 1. That's the lowest number. And if we divide by 1, we get 2 and 1. It actually doesn't change. So this is already in the smallest whole number ratio. Just to distinguish, a molecular formula gives us exactly how many elements we have in the compound. An empirical formula gives us the smallest whole number ratio. So last thing to think about is make sure that our ratio in each empirical formula is the same as that in the corresponding molecular formula, and that the subscripts are the smallest possible whole numbers. In part A, for example, the ratio to carbon, hydrogen to oxygen was 6 to 12 to 6, which is 1 to 2 to 1. I'm going to go ahead and stop here. I'll have a second part of this video posted up a little bit later.